All right, good afternoon, everyone. Thanks for joining us. My name is Riley Edwards, and on behalf of everyone here in Railtech at the University of Illinois, welcome to today's virtual William W. Hay Railroad Engineering Seminar. We've transitioned to a new system, and we look forward to your feedback on this new online system, and we're happy to field any questions about either the system or questions for today's presenter, Marcus Dersch, via the question tab inside of our interface here, or via email at heyseminar@illinois.edu. So if you have any questions for the speaker or about the system and its functionality, insert them in the questions tab or heyseminar@illinois.edu via email. The William W. Hay Railroad Engineering Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. On behalf of all of us, we thank US DOT, CN, BNSF, Hanson Professional Services, and Union Pacific for their ongoing support. It's greatly appreciated by all of us. We had a significant number of individuals register for today's seminar, upwards of 160, and these individuals are from a variety of organizations: A&M Railroad, Benesch and Company, Amtrak, the BNSF Railway, CN, CP, CTA, FRA, others at DOT, Jacobs, Kansas City Southern, Kiewit, KTH, Metro North, New York DOT, Pandrel, Patrick Engineering, STV, TTCI, and many others. And it's really exciting to have all of you with us today. To those of you that have already completed your PDH payment, you'll receive your PDH via email after the seminar. If you did not complete payment but wish to receive PDHs for your participation today, please send Emma an email using the payment link that was in the email that you were alerted to the seminar about. So for today's presentation, I'll give you a brief overview of what you're going to learn about. Today's seminar discusses a topic that's of critical importance in both terms of rail safety and state of good repair of rail infrastructure. Since 2000, at least 10 wide-gauge derailments have been attributed to broken spikes in track constructed with premium elastic fastening systems. Premium fasteners and timber crossties were introduced in heavy haul service over the past decades and have gained significant popularity given they are thought to reduce maintenance costs, rail rollover risk, and they generally do not require the use of rail anchors. However, given recent derailments and the identification of failed spikes during field testing at higher rates than have been seen with traditional fasteners, the University of Illinois is investigating the stress state of cut spikes in premium fastening systems. This presentation provides an overview of the broken spike challenge, documents the current loading environment, and provides an overview of mitigation methods that could be considered for reducing spike stress and the resulting failures that have been seen. Today's speaker is one of our own here within Railtech at Illinois, Marcus Dersch. Marcus is a principal research engineer here in Railtech at the University of Illinois, where he completed his bachelor's and master's degrees in civil engineering. His research was in railway engineering, focusing specifically on ballast performance and ballast performance improvement techniques. Marcus worked for Union Pacific as an engineering intern, and he's worked for Railtech since 2011. He obtained his professional engineer's license in 2015 and will become the chairman of AREMA Committee 30 later this month. Marcus's current research interests are railway crosstie and fastener design and railway ballast performance. I know you all cannot speak, but let's give a welcome somehow to Marcus for giving his seminar today titled Timber Crosstie, Spike Failures, Overview, Loading Demands, and Mitigation Considerations. So you can take it away, Marcus.
Thanks, Riley. And I can't see everybody, but it was definitely an impressive list to hear everybody that is on. And so I hope everybody finds it interesting, and I am looking forward to questions. It's been a team approach to being able to address this challenge that the industry is facing of broken spikes. I really want to thank Mateus Trizotto and Christian Cacciatorian, two grad students who are currently working on this project, helping put together the slides for today, as well as just doing really good work out in the field in the lab. And I also want to thank Tom Roadcap again. He was a previous grad student that many people knew that is graduated and gone on to join the industry. So, you know, this wouldn't happen without a good team. And that also brings me to wanting to acknowledge our sponsors of the Federal Railroad Administration funding this work, as well as a tremendous industry partner team. Each of the logos listed below, each of these companies have been able to provide time, resources, answer questions, let us get on track. It's just been a tremendous team being able to allow us to do the work that we've done that I get to present today. So I just want to thank everybody who's been able to contribute thus far. An outline of where we're going to be going today is shown on slide 3. And ultimately, I want to start at the beginning, being able to give an overview of the broken spike problem, summarizing what we know to date or what we knew a little while ago, and then be able to hit a big portion of our presentation today, which will be on what are some of these loading conditions that we see out in the field, vertical, lateral, longitudinal loads that are going into these components that end up failing. I'll then briefly highlight on some of our results that we've seen out at TTC. We had an opportunity to deploy a novel fastening system and compare it to a control fastening system to be able to look at how its performance, with tonnage. And then finally, I'll wrap up the conversation by hitting on some modeling results that shed some light on why we saw what we did at TTC, as well as give a couple other recommendations for how we might be able to mitigate some of these failures moving forward. So some background on these spike failures. I think we can very strongly assert that these failures are occurring due to fatigue. It's not a material deficiency, and this doesn't happen in just one type of elastic fastener. And it's not just cut spikes. It can also occur in screw spikes as well. So we believe this is overloading of the screw spike, leading to a fatigue failure, especially whenever we look at some of the failure surfaces. And Riley hit on this in the introduction. It's led to at least 10 derailments that we've been able to specifically link to this that's caused rapid gauge deterioration and wide gauge derailments. One of the most famous of which is the Mosier, Oregon derailment that occurred in 2016. If you notice in the bottom right of slide 5, where I'm highlighting, we have a very simplified version of how the load will be transferred from the rail to the cross tie. And in a system that uses spikes and anchors, a significant amount of longitudinal load will actually go through the rail anchor into the cross tie, and then some will go through rail plate friction to the plate into the spikes, but the majority in these anchored systems with no elastic fastener will go through that anchor. But we believe one of these driving factors that are leading to these failures within elastic fasteners is actually the loss of this anchor. And therefore, we now see an E-clip that is bringing that longitudinal load into the plates, which now the spikes and the plate tie friction now have to carry the entirety of that longitudinal load. To exacerbate this, or to increase the load magnitude on the spikes further, we know the wave action of the rail will actually lead to plate uplift. And so you will lose that opportunity to the plate to tie friction. And so these spikes, which were only taking a portion of that longitudinal load, are now being required to take the longitudinal load in its entirety, plus the lateral load, which has always been present. So if we want to think about this in a visual way, we can look at a hypothetical graph where we're going to be looking at the total stress into the spike, and then looking at different scenarios. And all of these scenarios, we're going to consider the threshold stress for where spike fatigue failure would likely occur. So for anchored track, that's tangent and flat, we would expect some level of longitudinal or lateral loads, but we'd expect this magnitude to be fairly low, definitely below the spike failure criteria. Once you go into a moderate or typical curve, the lateral loads would increase, but that longitudinal load is still not sufficient enough to be able to bring the fatigue failure or to cause fatigue failure to occur. But in the extreme circumstance, again, this is not an elastic fastener, this is a cut spike with anchored system. an extreme grade, extreme curve, or in special track work where the lateral loads are so high, you could go above this threshold for spike failure, and spikes have been found in these, or broken spikes have been found in these locations, but it is definitely not the norm. And so these anchored systems are everything to the left of this dashed line. And whenever we think about elastic fasteners, so we remove the anchor from the load path, we go back to a moderate degree of curvature, and we realize that this longitudinal load is now increased within the system. This is, again, just a way to visualize what we were talking about on the previous slide. And now we are asking the spike to take the same amount of lateral load, and we've increased the longitudinal load that leads to the spike failure. One mitigation approach that's been used by at least one railroad is reapplying anchors to these systems. It's believed that once you apply these anchors, the load path is going to be shared or taken by this anchor, and this sounds great in theory, but we know anchors do not always stay engaged. And so when they become disengaged, the longitudinal load increases, and it was shown to show positive benefits, so lower failure rates, and but it did not completely fix the problem. So the failure problem still occurred even in territory with anchors. So what are we doing at Illinois to be able to address these challenges? We're trying to take a holistic approach and being able to do work in the lab, perform analytical modeling, and being able to get out into the field to be able to measure what are the forces, what are the demands being placed on these fastening systems, as well as being able to get out to TTC, as I mentioned, and be able to test a novel type of fastening system to see, is there something we can change within the fastening system to help mitigate these failures? And so each of these components help inform the other, and especially the lab and the field are providing data into the modeling to make sure that what we're doing is representative of reality within those models. And all of this hopefully ties together so that we can make comprehensive recommendations on how to mitigate spike stresses. So I'm going to jump into the first thrust area that I want to talk about today, which is within the field of quantifying what are these demands placed on the system. And the high level outcomes are being able to know the demands, but also being able to provide data and information to the model. On slide 13, we have an overview of where we perform this field experimentation. I want to once again thank Norfolk Southern for their support. Brad Kirchhoff was very supportive of this effort, really helped us out. They provided us track support multiple days to be able to get out and install our installation. It was on a 3-track curve on Horseshoe curve, as I mentioned, in Norfolk Southern's Pittsburgh line. And this was just a great opportunity because what we had was the high rail of track 3 or of the westbound track with the uphills. So the high rail of these empty trains have seen the most failures of broken spikes at this specific location. Whereas the downhill loaded trains, they have seen failures, but not at the same rate as those uphill trains. And so being able to come to a territory that has different failure rates, but yet same curvature, same grade, same temperatures, climate, is a great opportunity to try to understand what's different. One of the things we're thinking about already whenever we're going there is, well, the tractive effort is going to be different. These uphill empty trains, the longitudinal load is largely going to be distributed within the locomotives themselves, whereas the downhill loaded trains will have air brakes applied and the longitudinal loads can be distributed throughout the entire train. And so we were really excited to be able to be supported by NS to get out onto their track to measure these forces. As I alluded to, we monitored and measured vertical, lateral, and longitudinal loads on the high rail and low rail of both tracks 1 and 3. A bird's eye view of our site is shown on slide 15 with additional information about each of these tracks. We can see the grade, curvature. It was a lubricated curve. and it's an air brake grade. And you can just see a zoom in of our site on slide 16, where we have our instrumentation placed in the cribs for our loads. And we were capturing displacement data as well, but I will not be highlighting that today. Jumping into the results on slide 17, I'll first orient you to this figure. We're looking at a percent exceedance graph where we have percent exceeding on the vertical axis, and we have vertical wheel load on the lower horizontal axis and vertical rail seat load on the vertical horizontal axis. And we are taking the vertical rail seat load to just be 26% of that vertical wheel load. And that's assuming a 3,000 pounds per inch track modulus, as well as standard size or regular sized axles. We use the locomotive wheels for the diameter. And we came up with, using Talbot's approach, we came up with 26% of that wheel load going into the rail seat. And the first thing that we'll notice is that the vertical loads on track 1 are indeed higher than on track 3, which is to be expected. They are loaded trains, and so their loads should be higher. And a way to read this figure is if we look at 60% exceeding on track 1, so 60% of all loads exceed about 25 kips. Whereas on track 3, we're going to see that it ranges from 10 to 15 kips at 60%. So there's greater loads on track 1 than track 3. The other thing that becomes apparent is that the track 3 operations are leading to an underbalanced condition, where on average, the low rail has 30% greater loads than the high rail. Or another way to think about that is the high rail is becoming more unloaded than the low rail. Another way to visualize this and understand kind of the operations at the location is looking at slide 18. We turned the percent exceeding figures into box plots. It allows easy comparison of the medians as well as the variance within the data. And we still do see this, the medians are different. So this shows an unbalanced operation condition on track 3. But one thing we notice when we look at our balance speeds, which they are below the median, and most of the data falls below the balance speed, which can be seen on the right hand of slide 18. We see that track 1 is also operating below balance speed, which makes us wonder, was there actual proper super elevation as provided by Norfolk Southern, or is there something operationally that it's going on that is causing this balance within the vertical loads? But I think one of the big takeaways that we're seeing from this is the high rail of track 3 has the lowest vertical load, which can definitely play a role, and we'll get to that as we move forward. And as we move forward, we'll look at these lateral wheel loads. This is the same representation of a percent exceeding versus our lateral wheel loads, lateral rail seat loads. And in this instance, we're taking 35% of the wheel load to go into the rail seat, and that's based on the literature of what is expected, the lateral distribution to go into the system. Similar to the vertical load, we once again see that track 1's field facing or outward lateral wheel loads are greater in magnitude than in track 1 is greater than track 3. And the other takeaway is that track 3 high rail has the highest percentage of gauge facing lateral loads. And that was something that became even more apparent whenever we looked at leading versus trailing trucks. And so there's definitely something we still want to dive into this data a little bit further to understand, but we already are saying that track 1 has greater demands vertical and lateral compared to track 3. But again, this is to be expected given the loading of the cars. Slide 20 is just showing a box plot of the similar data, being able to help better visualize, again, the variance of the lateral load and be able to see where the median is truly falling and how this data is scattered on tracks 1 and track 3. The longitudinal load is definitely different. It's something that we think about more of rail neutral temperature, or understanding and managing the stress state of the railroad is whenever we think about axial stresses or the longitudinal stresses within the rail. But what we wanted to do is be able to understand what is the effect of a single wheel? What is the effect of these passing trains? The longitudinal effect on the fastening systems around the track. And so thinking about this from an axial load perspective or a rail load perspective, on slide 21, we can see that there's compressive forces behind the wheel and tensile forces in front of the wheel, if we're imagining that the wheel is traveling in this direction. And this is important to realize. This information comes based on a book from Kerr from 2003. We just can see this distribution of forces, compressive and tensile forces. And this makes a lot of sense of compressive and tensile forces. But once we think about what does the fastener feel, we now realize that the fasteners are all providing forces in the same direction. And therefore, this made us want to look at the data in superposition instead of a single wheel. We really wanted to start thinking about when multiple wheels are acting next to one another. And so when we look at the superposition of these axial loads in the rail, we've taken a simple case of two locomotives. First locomotive is in red and the second locomotive is in blue. And we see that there is an additive effect in front and behind these sets of locomotives, but in between, in this black line, these forces actually cancel one another out. The tensile and compressive forces cancel each other out. And so in between the locomotives, there's actually zero additional stress added due to these locomotives, which is the opposite of what we see with the fastener forces, where in between these same two locomotives, when we think about the superposition of all of these wheels from two locomotives, the fastener loads become additive. Again, you can see locomotive 1 in red, locomotive 2 in blue, and the combination in black. And our maximum fastener force is now between the two locomotives. And so this was just good information to realize, helps calibrate our mental model of how these loads are being applied to the rail as well as to these fastening systems, which is what we need to know to be able to improve design or make recommendations. One thing to keep in mind about these longitudinal loads and placement is that these waveforms are much longer than what you would expect from vertical and lateral loads, which occur basically right underneath the wheel. The longitudinal loads are being applied out in front and behind these locomotives. And so you will actually get, these are highlighted yellow regions of where you could expect plate uplift. And we have videos that confirm that plate uplift occurs with these elastic fasteners, which are attaching the rail to the plate. Instead of having the plate or the rail rise up from the plate in a conventional spike and anchored system, this elastic system pulls the plate up from that tie. And so we're applying longitudinal loads at the same time that there's plate uplift. And so that introductory slide that shows that this load is now being carried by all the spikes can be better visualized of why that's occurring, because these longitudinal loads are being applied when there is uplift, which is not the same case for the lateral loads. For more information of this approach to being able to go from a single wheel to superposition of multiple wheels, we have developed a paper and it's currently under review, and the information within should be able to help others better understand our approach in more detail. One other consideration is that since it is additive of having two locomotives next to one another, investigating the effect of distributed power, whether this is a single tender or it's multiple units being split within a train, once you introduce even a single car in between two locomotives, we see a reduction, and in this case, of 40% of that fastening force that would be going into any of the spikes or going into the rail seat. And so that is very important to realize that there are things that we can do to reduce the forces that go into our fastening systems. So when we actually quantitate or look at the numbers that we got from the field, we can see track 1's values are lower than track 3. In actuality, track 3 has 50 to 70% higher forces in the rails. But I want to pay attention to the magnitude of loads that are going into the fasteners. And keep in mind that the vertical loads are transferring approximately 25% of the load to each individual rail seat. The lateral loads are transferring approximately 35% of the load to each rail seat. But when we go from rail longitudinal loads to fastener longitudinal loads, our order of magnitude is dropped by at least 1. And so we're seeing less than 10%, or maybe approximately 10% of those longitudinal rail loads are now going into those fasteners, which is, again, different than what the vertical and lateral loads and how those are distributed. And in this case, again, longitudinal loads on track 3 are greater than track 1. And we can keep in mind that these longitudinal loads are being applied when there is no friction, when there is complete uplift. And so the entirety of the longitudinal load would be applied to these fastening systems. I want to summarize the lateral and longitudinal fastener forces. Part of the reason why is to realize that it doesn't answer the full story. We haven't completely isolated why track 3 high rail has greater failure rates than track 1. For example, if we were to look at the 90th percentile lateral loads and the 90th percentile longitudinal loads on track 1 and track 3, we would expect fatigue failures on every rail. But in all actuality, we see most failures on the high rail of track 3 and some on the high rail of track 1. And so that still leaves some questions in our mind of exactly why that's happening. And we believe that we really want to look into the effect of the vertical load and the friction. I do have conclusions that I won't read through on slide 29, but speaking towards this future work, we do want to investigate these effects of operational characteristics. And what I mean by that is that unbalance on track 3 leads to lower rail seat loads. And the median rail seat load, vertical rail seat load on the high rail of track 3 was only 3 kips. And so that means that the frictional capacity at that rail seat is much lower than the frictional capacity of the other rail seats that have higher vertical loads. And so these are things that we really want to be thinking about and looking at moving forward, is how can we encourage additional friction, or how can we investigate this problem a little bit more. And to think about this hypothetically, on slide 30, we're trying to show if you were to take the lateral and the longitudinal forces from the table before and you were to add them together. These are the magnitudes that you might get. Any one rail seat might, 90th percentile, for example, might see 3 kips or 3.5 kips or whatever it might be. But on track 1, where the vertical loads are higher, friction can take greater portions of that lateral load because you have higher vertical pinning, which can enable greater frictional resistance. And therefore, the longitudinal load stays the same, but the lateral component that's going into the spike is lower. Whereas on track 3, it's a lower version of vertical load, or lower magnitude of vertical load, and therefore less friction is enabled and greater forces are actually going into the spikes. Again, this is just a hypothetical representation. We have been looking at this in greater detail, but it's definitely the direction that we want to continue to go to figure out what is finally or truly driving these failures in the high rails of both tracks, but more often the high rail of track 3. So moving on to the next field investigation we had, which was, can we assess the performance of a novel fastener? And so we went out to TTC. Our control zone consisted of E-clips and cut spikes and was 20 cross ties long. And our test zone, so this novel fastener, which is used in Europe, but just not very much in North America, consists of tension clamps, which can be seen on the bottom picture, as well as on the right-hand side of this middle picture, with screw spikes and spiral washers. And what we believe is the main driver between the difference of these two systems is definitely the spiral washer. The tension clamp does play a difference. I'll get into some of those results, but the spiral washer is playing an effect, and I'll hit on why in just a slide or two. The test occurred between fall of 2019 and summer of 2020. We accumulated 170 MGT, and we performed visual inspections every few months. And track geometry was measured after the fall and spring season, and loaded gauge using a portable track loading fixture also occurred to help give us an idea of how the system was behaving upon lateral load application. Based upon our visual inspection, our control zone saw 6 broken spikes, whereas our test zone did not experience any. Whenever we think about loosened components, there were multiple spikes. Not only did they break, but some of them uplifted from the plate slightly. Whereas in our screw spike, or in our tension clamp zone with spring washers, we saw 3 spikes that had backed out 30 to 45 degrees of rotation. So that's 1 to 1.5 millimeters at 60 MGT. There were indications of additional loose screw spikes after 170 MGT, but again, only on 5 rail seats. And I don't have the ability to be able to go into as much detail as I did in terms of looking at the amount of rotation that occurred on these spikes. So this would indicate that there's a potential for additional tightening or maintenance that would be required if you're using spring washers, because things could become loose. But even with this 1 to 1.5 millimeters uplift that we did see, or rotation that we did see, we still estimate that the spring washers were still able to apply between 2 and 3 kips of clamping force that they were originally applying. Skewing ties with the control system was fairly significant. They had to go out into the field and reset these ties multiple times, whereas in the control zone, it was done minimally. And it could be because the shoulder of the control system was circular and not square, which could cause additional rotation of the system, which could lead to skewing of the ties. But it's definitely something to note in this specific example of things that we noticed that were qualitatively different. When we further dive into our data, we were looking at base gauge and kind of head or gauge widening at the base as well as at the head, and really trying to understand what is different between these two systems. And one of the things we realized is that the system with spring washers really encouraged this plate to cross tie contact and gave very consistent and low values of base gauge, which can be seen in this top right figure, whereas and also provided very consistent clamping force and thus increased lateral and rotational strength and stiffness whenever you're applying the outwards lateral loads. And whenever we look at box plots for variability, we just see additional scatter in the control compared to this tension clamped spring washer system, which is able to reduce variability. And when you can reduce variability with how load is transferred, it also reduces the amount of variability in what the spikes are feeling and being subjected to. And these data were taken, we have the test in blue, our control systems in red, and they were both taken in December as well as after June, so after the fall season and after the spring season. And this brings me to my last topic, which I'll be hitting on, which is giving an update on what we've been working on with our analytical model. And some of the motivation for the analytical model was being able to better understand the mechanics of why that one system worked better. Can we quantify the effect of that spring washer? But there are other reasons behind it that I'll get to after just giving an update of, we've had this model for this novel spike and timber model for a couple years, and the first thing that we were able to find with it was that the longitudinal load is more detrimental than an equivalent lateral load. And to put that another way is, if you were to apply 2 kips of lateral load, you would get a lower stress response from your spike than if you were to apply 2 kips of a longitudinal load. And this is due to the fact that timber is less resistant, or is weaker in that direction than it is the lateral load direction. The perpendicular to grain strength, which would be resisting the longitudinal loads, is lower than the parallel to grain, which would be the lateral loads. And so this is important to realize, that you don't even need as high of a longitudinal load to lead to failure. We also just were able to quantify that stress can exceed that fatigue limit at regular service loads. Maximum stress varies with the magnitude and direction of the load, and species of timber does affect the depth and does affect the magnitude of stress. But we've taken that model and we've advanced it a little bit to be able to actually start answering these questions of, what can we do now? Okay, we understand there's a problem. We've been able to quantify somewhat of why that problem happens, but what can we do within the fastening system design to mitigate the stress, to be able to reduce the stress and mitigate failures? So these are 6 studies that we jumped into to be able to understand, what can we do? For time's sake, I'm only going to hit on 3. And I will allude to the results from the others, and there is a paper that's coming out that will have a more detailed response from all of these as well. But before I go into the results, just an overview of what the models did look like. From a very high level, each model was built to answer a specific question. Our model on the left is a single cut spike that was driven into a timber tie, and we use this to quantify the effect of cross-sectional area, the effect of load magnitude, the effect of load location. It also just gives us the control of what is a cut spike feeling in a timber tie. The second model, which is seen in the middle, was really built to answer the one question of, how does the performance of a screw spike compare to the performance of a cut spike? So we can actually answer the question of, is there any performance difference between cut spikes and screw spikes? The final model that is built and shown on the right is a single rail seat model, and this is a half timber tie with a modeled plate and multiple spikes that are driven into the plate. And we're able to quantify answer various questions with this, but specifically what I'll be highlighting today is, what is the effect of the spring washer or a clamping force between the plate and the tie on spike stress. So just a little bit of background on why we wanted to investigate the performance differences between cut and screw spike. The performance difference between cut and screw spikes, we can see slide 39. And we know that multiple railroads are actually already moving from cut spikes to screw spikes. But we also know of one railroad that has moved from screw spikes to cut spikes. And some perceived advantages, some conversations that we've had with people within the industry mention that screw spikes have, or perceived to have, higher bending strengths. And they also can have increased plate hold down strengths, which is great. But if we put together a table of just some properties, some geometrical properties of these spikes, we have a cut spike, the upper shaft of a screw spike, as well as the threaded region of a screw spike. And if we take the information that's provided and we quantify their moments of inertia, which are also seen in this column here, or in this row here, we see that the upper shaft of the screw spike does have approximately 3 times the moment of inertia as the cut spike does. So you should see or should expect improved bending strength in the upper shaft. And this is all based on just the simple analysis of MC over I, where as you increase your moment of inertia, you should decrease the expected stress. And so this is 3 times larger. This value isn't significantly different, and so you should be able to expect improved performance. However, whenever we look at the cut spike versus the threaded region of the screw spike, we actually see that the moment of inertia is quite similar, and therefore our resulting stresses are also more similar. And so our expectations, just by reviewing this geometry of what these spikes look like or how they are made, actually says, yes, you should see increased bending strength in the upper shaft. However, there could very well be decreased bending strength in the threads and therefore increased stresses at equivalent loads. And so that is why we wanted to continue this study and look at it further. And so qualitatively, whenever we look at these results on slide 40, we've subjected each spike to 2,500 pounds of longitudinal load. The first thing we notice is that the stress distributed within the cut spike is over a larger area compared to the screw spike. And that's because of this tapering down to the threaded region. We now have a stress concentration. Further, we see that the maximum spike stress depth, which is approximately right here, for the cut spike is 1.5 inches below top of crosstie, which aligns very well with the field performance. Whenever you go out and find broken spikes within the field, they will be on average 1.5 inches below the top of crosstie. Our screw spike depth is lower because, again, this upper portion of the shaft is larger. You won't see as high bending stresses, so it's going to push it down further right to where the threads occur, and it's about 2 inches, and that 2 inches in this model is right around the first set of threads, and that is where the failures have also been seen in the cuts or in the screw spikes. This gives us additional confidence within our model. And whenever we quantify the maximum stress, which is on the vertical axis, versus the longitudinal force that is applied, below 2,000 pounds, we see little to no difference between the resulting stress between the cut and the screw spike. And in fact, there's less than 10% difference between 2,000 and lower. But beyond 2,000 pounds, there is a rapid increase within the screw spike compared to that cut spike. And we do believe that's because of the stress concentration, because of this changing geometry. But for all intents and purposes, most spikes will not see greater than 2,000 pounds longitudinal force application. And therefore, whenever we think about what are the performance differences between cut and screw spikes, there really is no expected behavior difference or performance difference when thinking about bending only. Screw spikes definitely have a benefit of being able to have better plate hold down. There are benefits, but if we're thinking about bending strength, for this specific case, that should not be a consideration for going from one to another, but there are definitely benefits. So definitely take the other benefits that come along with screw spikes. The next study I want to hit on that our model was looking at was this normal clamping force, or the effect of that spring washer. And again, the goal is to ensure that the load is transferred through friction as well as the spike. We really want to keep that plate engaged with the tie to allow friction to take some of the work. And therefore, we have to be able to account for this wave action of the rail. And so the proposed solution that was used out in the field is a spring washer. And so that's what we wanted to model here. I'm showing on the right-hand slide of slide 42, just an example load displacement behavior of one of the spring washers that was used out in the field, and we've also looked at in the lab. And one thing that I'll note is that there's a very steep slope, or a very high slope, in that very small changes in deflection or uplifts of a screw lead to large changes in the applied force that's going into your fastening system. And that's something that could be, or design could be reconsidered in making something more compliant or having a greater working range of being able to apply a specific load as opposed to having such a high magnitude. And we'll come to see why. For this specific study that I'll be showing on the next slide, we investigated what is the effect of applying 3,400 pounds per spike spring washer, as well as 1,000 pounds per spring washer. And the thought behind this was you're never going to achieve your, or you will rarely always achieve your maximum applied load, which might be between 5,000 and 7,000 pounds per spring washer per spike. And after time, there's going to be either minimal or minor plate cutting, or as we saw out in the field, backing out of these screws, which will lead to a reduction in that spring washer force. And so we wanted to look at these two magnitudes, which also seem to be very reasonable of what spring washers could apply. Our plate and fastening system is has a visualization where we have spikes 1, 2, 3, and 4 in blue, red, green, and yellow. And we applied a longitudinal force to the plate of 2,500 pounds. We looked at 3 conditions. The first condition was whenever there's 0 clamping force, this is our control, and the nominal stress was 1. The nominal average resulting stress was 1 within these spikes. When we applied 1,000 pounds of force per spring washer per spike, we were able to see a 70% reduction. And whenever we applied 3,400 pounds per spike, it was an 80% reduction. So this was a non-linear response between of what it took to be able to reduce the stress that was going to these spikes. And this brings me back to the point of you don't need significant, based on this analysis, you don't need significant spring washer forces, the 5,000, 7,000 or greater forces per spring washer. 1,000 pounds per spike gets you a 70% reduction in the stress, which could be sufficient. It could be all you need. So having that greater working range, that displacement, could account for additional plate cutting or additional rotation, and would limit the amount of maintenance that would need to be performed to keep the system tight and actually receive any of the benefits that these spring washers are providing. Moving to my last mitigation method that we were able to look at with this model is spike engagement. And just a brief background on why is we know that the plate hole tolerances are larger than the spikes, and that the potential displacement when load is applied to these spikes or to these systems will likely not engage that spike if it wasn't engaged to begin with. I have specific numbers listed on this slide to show how much larger the holes are than the standard cut spike. So it's reasonable to believe and see that not all spikes will be in contact or will not have the same level of contact at any one time. And this has been documented also in the lab from our lab studies, as well as others have performed work out in the field. Randy Bowman of NS and TTC have also quantified that there is a non-uniform distribution of forces within the spikes, and it makes sense because of these tolerances. And what I mean by engagement on this next slide, whenever I talk about we disengage the spike, we can see for people following along online, you'll see that if we have a vertical load that's being applied from the top of the slide coming down, this spike would be engaged. It is within the load path. A disengaged spike, by our definition, is when that spike is moved. It stayed within the fastener, but it's been moved to the opposite side of the tolerance of within that hole. And now that same load, which is coming from the top of the slide to the bottom, the spike is no longer within that force chain and therefore not going to provide any support until the plate moves the sufficient amount to close that gap. So it is disengaged. So when we look at the results in slide 45, the effect of spike engagement with the plate, we have the same system, spikes 1, 2, 3, 4, 5. Our control is on the left. Again, we're looking at the nominal case is when the stress is 1. What happens, or how does the stress change as we disengage a spike? So our legend is furthered by a spike is within the load path or engaged when the background is white, and it's disengaged when the number background turns black. So for example, spike 1 is disengaged in this instance, 2, 3, and 4. And so the first thing that we notice is that when this spike is disengaged from the load path, it truly acts as though it was removed from the system. And I want to reiterate, the spike was still within the model, but the displacement was not great enough to re-engage the spike. The other item that we notice is that the load is not evenly redistributed among the spikes. For example, when we remove spike 1, the load is not redistributed, or the stress is not redistributed to spikes 2, 3, and 4. It's largely redistributed to spike 2. And the same can be seen whenever we remove 2, 3, or 4. Largely, that stress is distributed to the spikes adjacent as opposed to all spikes evenly. And to put a number to this, whenever we disengage spike 1, there was a 140% or a 2.4 times increase in the spike stress of spike 2. And so this is important to realize that these tolerances do have an effect. And if there are design changes that can be made to encourage engagement, then that's something that's worth considering. But this has to be, of course, balanced with constructability and everything else that goes into it. But it's very important to realize that there is an effect, and this can lead to non-uniform loading within of the spikes. So some of the conclusions, again, a disengaged spike can lead to large increases of the other spike stress and is not uniformly distributed. A clamping force of only 1,000 pounds can reduce the spike stress by 70%. And there's little difference in performance difference in bending between cut and screw spike strengths, especially below the 2,000 pounds applied longitudinal load. Bullets 4 and 5 are from the studies that I wasn't able to highlight, but the full studies as well as those results will be presented. A draft has been submitted, and we're currently working on addressing comments and moving this paper forward of methods to mitigate railway premium fastening system spike fatigue failures using this FEA approach. So whenever we take into account lessons that we've learned from the work out in the field and what we've seen through the model, we can make recommendations to mitigate spike failures through operations as well as through fastening system design. And through operations, we want to consider reducing these longitudinal demands when feasible by distributing power. We saw that reduced the demands on the fastening system itself, and evenly distributing the tractive effort among multiple units. These slave units can try to improve upon how everything is evenly distributed among them, among every wheel that's on the train. And then we want to reduce the lateral forces through proper gauging. In curves, you can increase the gauge slightly to be able to reduce those lateral forces, or through top of rail application. As we reduce lateral and longitudinal demands, that will decrease the demands on the spikes. If we can operate near balance speed to encourage the equal vertical loading on high and low rail, or get away from that condition on the high rail being loaded, which we saw on track 3. Again, the median load was only 3 kips on that high rail, which means there's not a lot of frictional capacity to be able to take that lateral force into the discipline. Through fastening system design, some considerations we can take are encouraging engagement between the plate and the crosstie. Screw spikes do a good job of this upon initial installation, but if they were to back out, you lose that benefit. So spring washers are one option. They definitely lead to additional challenges with installation and additional would be worth it, and it's definitely worth looking at a little bit more, or being able to see if we can improve upon it a little bit further. We also want to encourage the engagement of all spikes within the plate. Again, being able to change the design or be able to change tolerances when feasible to be able to better encourage that all spikes be engaged could definitely reduce the amount of stress that any one spike feels. And then one last thing is increasing the size of the spike, increasing its bending strength to account for any additional loading. Could also be an easy fix that doesn't really change maintenance practices. It just changes the design and changes the plate, which has its own challenges, but it's definitely something that is feasible to do. So once again, I do want to thank the Federal Railroad Administration for funding this work and continuing to sponsor and support us, as well as once again our industry partners for, again, just answering questions, providing materials, giving us track time. It's just been really supportive to have this team. And with that, I want to say thank you, and I'll open it up if Riley, if there's any questions to be able to address.
Marcus, thanks for a great presentation. Thus far, no questions have been submitted. I'd be happy to receive some now. While we wait to see if any questions come in here at the end, I guess I have one question for you, which is one of the things that strikes me in today's presentation and that I've learned from you throughout this work is the relevance of engaging our friend friction to help us solve this problem, or at least mitigate the effects. Are there lessons that we can learn from other types of cross ties and fastening systems and track systems such as direct fixation that could inform how we go about answering these questions or investigating this?
Yeah, I think that's direct fixation is definitely a good example where you're really clamping these systems down and really trying to allow friction to be your friend, to take advantage of that, to transfer these loads within the system. So I definitely think there's something that can be learned there. And whenever we think about other failures, we think about the movement of the systems. Rail seat deterioration leads to abrasive conditions between a plate and a concrete tie. Plate cutting beyond high stresses is also driven through movement of the plate relative to the tie. And so anytime we can reduce this movement, it typically leads to benefits and improved performance, regardless of the system.
A good answer. Thanks, Marcus. We have a question. Have you considered the effect of in-train forces on rail seat loads at Horseshoe curve? Could this explain why the loads on the low rail of track 3 are higher than those on the high rail?
I think that's a good question. We tried to look at kind of the force profile throughout. We've tried to look throughout the train to be able to see how the forces are being transferred or what forces are throughout the train. The main thing that stood out was the lateral load from pusher locomotives on the downhill side. So on track 1 coming down, created significantly higher lateral loads than the lead locomotives. And so that's the one thing that I can remember that stood out of in-train forces, or of the forces throughout the distance of the train. Have not specifically looked at kind of buffer draft forces or anything reported from the locomotives. I think that's something that definitely we could consider or look into.
Very good. Thanks for that response, Marcus. One more question is, and this is a good question, how do we actually encourage spike engagement? Is it something that we can actually correct after installation?
Yeah, that's a good question. And after installation, how can you encourage it? I'm not sure, without putting some sort of filler in between them to be able to encourage that engagement. After the fact, I don't know of a good way to do that. But beforehand in the design, perhaps there's a washer system or some kind of material that can be pushed through that allows better engagement, or you change geometries of somewhere. But afterwards, I can just think of somehow filling in the voids, but it sounds like a messy problem and quite difficult.
Very good. Thanks for the response, Marcus. And we have one more question that's coming in. Hang on 1 minute. Would you expect a significant change in these research results if the ballast conditions were muddy instead of well-drained, such as having pumping track?
Yeah, no, that is, I like that question. And we definitely know that ballast condition plays a large role in in all force transfer. It definitely changes your modulus of track in the vertical direction, which will affect the distribution of forces, but it also is going to affect your longitudinal track stiffness. And as your longitudinal track stiffness becomes lower, your fastener forces will also become lower. And as your longitudinal track stiffness goes up, your forces will go up because things aren't able to be distributed as well. And so if there's muddy pumping track, that's not good for a lot of reasons, but I guess you're reducing your modulus and helping distribute forces, which could be a benefit to the spikes, but definitely not a recommendation. I think it would just lower the magnitudes of forces that each fastening system or each component would feel. But definitely not good for a host of reasons.
All right, we got a couple more questions here. One is there any study that that you've conducted looking at PVC or plastic ties, so presumably composite type ties?
We have not addressed that yet. We do think there are potentially perceived benefits from composite ties, specifically whenever we think about compressive strength of composites. You might not get crushing of the timber. Whenever we talk about the strength of timber being different in the lateral versus longitudinal direction, it should be homogeneous regardless of direction with composite ties. And if the composite tie has greater strength, compressive strength than timber, then you also should get less bending as a result within your spike, and therefore stresses should decrease. And so it's nothing that we've looked in great detail, but it's definitely on our list of items to be looking at moving forward, is benefits of composites or performance differences between timber and composite. Good question.
Wonderful. And then I've got one more question, then I'll wrap us up for the day. Do you think that the spikes between trucks have more severe loading environment than the spikes under the wheels, based on the longitudinal modeling that you've done?
No, I don't. And I think that's when the plates really can move around more. But underneath or between the trucks, you're not going to have the lateral load application. And I do definitely want to make it clear that longitudinal loads by themselves are likely not driving these failures. It's a combination of lateral and longitudinal. And so maximum forces are still likely underneath a wheel. And that's because the longitudinal load is being applied during uplift. It's being applied consistently kind of throughout the duration of the train, but it just pins that plate up against the spike longitudinally, and then the wheels take that lateral load and really just kind of bang that plate laterally into the spike. So you kind of pre-stressed it with the longitudinal load, and then you nail it with the lateral load. That's I think the dynamics that we're actually seeing within the system.
Good deal. Thanks for responding, Marcus, and thanks for kicking off our fall 2020 Hey Seminar series. This was really a enjoyable presentation, and I think you should assume that everybody is applauding loudly from their home offices right now. We appreciate you doing this, putting it on today. I hope everybody is able to join us in 2 weeks on Friday, September the 11th. That'll be our second Hey Seminar for the fall semester. We have Richard Fox-Ivy from Railmetrics, Inc. will be presenting. His seminar is going to provide an overview of some ongoing FRA R&D work that some of us here at Illinois have been fortunate to partner with them on, that involves the development of railway asset change detection technology using 3D laser scanning and an artificial intelligence approach. So we're excited to have Richard present in 2 weeks. Thanks again, Marcus, and everybody have a nice afternoon and a safe weekend.
And I see a question from Joe Riley. And can I address that one just real quick?
Sure.
Since I saw it, Douglas fir definitely is. If I recall, Douglas fir has lower strength and therefore likely would have higher bending stresses within their spikes compared to a conventional hardwood. But I'd want to go look at those specific values. If you send me an email, I could probably go and find the specific values and kind of give you a better answer. So
thanks, Marcus, and thanks everyone. Have a great rest of the afternoon and weekend. We'll sign off now.
Thank you.